structure looks like this. Okay, so over here, this is our point B. Okay, so let me write down some key geometries. So if I would look at some key geometries, we have over here to here is, wait, yeah, this is 6, this is 2, right, and then 0.5, and then here to the bottom is 6, right, and then the width is what? The width is 6, so this is 7, right, this is 7, 6 plus 0.5, 7, and then the top part 6, 7, 11. Right, the top part over here is 6 plus 7, 7 plus 1, 11. Okay, so it wants to find the shear flow at point A and point B, right? So we construct, so we know that we have a V, right, coming from the center, right? And then I'm going to draw the axis of the shear force. Yeah. So this is the axis of the shear force. Okay. So now, the centroid. Okay, I'm not going to calculate the centroid. I'm just looking at is 2.8362 from the top. Okay, so 2.8362 from the top. Okay, so this is our centroid. Right, so from here to here is 2.8362. Right, so again, we construct our shear flow. Okay, so the web controls the direction of the shear flow, top to bottom. Okay. And then we have a terminal over here, right? So the terminal does this. Okay, I'm going to stop down there. Now, at the A section down here, right? At the dot where I'm going to write, these two are also what? Terminals. Okay, because if you look at where I just draw the dot, or I'm going to highlight the dot over here. Now it's like a what? It's like a white flange. Yes or no? It's not a box beam, right? So the shear flow will do this. Okay, and then after that it will come back here. So this is our terminal. So this question has 4 terminal, right? Terminal 1, terminal 2, terminal 3, and terminal 4. All right. So by looking at the arrows that we have drawn at A, point A, right? At A, which is over here, this is the area that we need to consider. Why? Because it is a what? At that section, it's not a box beam, but it's a what? White flange. Okay, so we are going to do white flange analysis. So Q at A, right? So I hope you all can see that. Okay, so there is a white flange. So the Q at point A is equal to the width is 2, the depth is 0.5, the y bar is equal to 2.8362, 2 point what? 2.8362. Okay, hold on. 2.8362 minus by 0.5 divided by 2, right? So this is equal to 2.8362 minus by 0.5 divided by 2 times by 0.5 times by 2 is equal to 2.5862 inches cubed. Okay. Right? So this one is only Q, right? So if you look at this value, is exactly the same like what we got, right? So at point A, if you look at the way they calculate point A, they did not need to divide by 2 down here because it is what? They did not need to divide by 2 down here because it is a wide what? Flange. Okay, right. So the next one at point B, what is the area that you have to take at point B? So now, so we apply rule number 5. Then we have to go back to our number 1 to 4 rule, right? So the number 1 to 4 rule is the analysis starts from where? So analysis starts from Y max, right? And then this is the analysis direction, right? So the analysis, it pull back. So the area that we have to be concerned about, it is this area now. Okay, so I think this is more easier now, right? It's the A that's confusing, right? So the first moment area of point B, right? So you know that there's 2Q, yes or no? So Q coming in, Q coming in. So this is a box beam analysis, right? And you have 2Q, right? But so Q at point B. So the width is 7. The depth is wait, let me see the depth. Is 0.5. Right. Then we have the whole thing is what? The whole thing is 6.5 minus by 0.5 divided by 2. Okay. So this is equal to 6.5 minus 0.5 divided by 2 times by 0.5 times 7 is 21.87. 21 point, wait, I got it. 10.93. Wait, there's something wrong with my area. Hold on. 6 plus 0.5 is 7.25. From the top is 6.5. 6.5. So wait. I think I know the Y bar. I got it wrong on the Y bar. So this is equal to, so the whole thing is 6.5 minus by 2.8362, right? So the whole thing is 6.5 6.5 minus by 2.8362, then you minus by 0.5 divided by 2. So what I've done over here is I want to find this distance down here. All right, so this is 6.5 minus by 2.8362. Okay, so close bracket. So 6.5 minus 2.8362 minus by 0.5 divided by 2 times by 0.5 times 7 is equal to 119483. So this is the same. Okay, 11.9483 inches to power 3. Right? And you can see at point B, they have to divide by 2 because you have what? You have 2Q. Okay. So this example is a combination of like the head, okay, that we did the example in class on Tuesday. Okay, is if you combine both white flange and box beam. Okay, I hope this make it clear for you, like how to find the first moment of area. Okay, Now, the next one. Okay, now this question, it is the most confusing. Okay, the most confusing. Okay, so the most confusing in the sense that how does the shear flow now? Right? Okay, so we are still going to apply what we've learned, and this is the I I I I don't recommend, like, if you look at the solution, is very confusing. Okay, you have minus first moment of area, which I've never taught you guys all this before. So I want you all to apply what I have taught you, more important than anything else. Okay, more important than anything else. So that's why the solution manual, when you see the solution manual, don't try to figure it out. Okay, rather use or apply what I teach you. Okay, okay. So, but like all the first moment of area, all this value, okay, has to be somehow related with the technique that I have taught you. Okay, so don't worry about what is this minus sign going on. Okay, don't worry about it. Okay, I don't want to. So apply what I've taught you is more important. Okay, now this problem is unique. Okay, and it is you can say very confusing. Okay, it's unique and it's very confusing. Okay, so we are going to make the assumption. Okay, we're going to assume. Okay, we're going to assume. Again, this is to determine the shear stresses at the 5 points. Okay, so we're going to assume. Okay, we're going to assume the centroid. All right, the centroid to be at the center. Okay, so that's the first assumption that we make. Okay, I know it's not really as a center because there's a gap, but we're not given the distance of the gap. Okay, we're not given. So this is our centroid. I'm going to draw a straight line first. Okay, so this is our centroid. Then we are told that we have a shear flow. Right? Sorry, we have a V. So we have a Vy. Right? Then I'm going to draw the axis of the shear force. Okay, so this is the axis of the shear force. It's exactly at the center. So for this case, it's interesting. Okay, is because you see how we construct the shear flow. So the web controls the direction of the shear flow. Then, okay. So you ask me, Eugene, there are 4 webs down here. Which is the main two? So the major web will always cover the top and the bottom of the structure. Okay. So I'm going to draw the shear flow of the major web. Okay, that is the shear flow of major web. Right? And when that's the case, we will know that the shear flow will move this way. Right? So this is the terminal. Right? Then at the bottom part, it will move this way. And this is unique because this is the first time we are seeing a reverse flow at the top or at the bottom of the structure. Yes or no? Right now the flow gone reverse. Yes or no? Gone opposite. Okay. Right. Okay. So point E is easy to find. Yes or no? Right. Point E is easy to find. So at point E, right, we're going to do the easy part first. Okay. This is easy peasy. Even point D is easy peasy, but we can make it difficult. So you look at point E, right? We are going to look at this area down here, right? Because you have Q going one side and Q going the other side. So this is straightforward, right? So we're going to find the Q, right? So what I'm going to do, there are information that are given. We're not going to find them. So I'm going to write IZZ is equal to 133, or what was on there. They use what value? I'm just going to use their value, okay? 133.75. Okay, so that is the value. And the thickness is 2 millimeters. Okay, so we are given thickness T 2 millimeters. Okay, right. So we are going to look